I'm Paul He from the University of Pennsylvania, and I'll be presenting work done with my advisor and collaborators at Galois. Verifying imperative pointer manipulating programs is an important but difficult task. For full functional correctness, separation logic tools for mechanized proofs, like VST and IRIS, are the gold standard. They can prove very expressive properties about imperative code, but they're also very laborious to use and require expert knowledge. One reason for the difficulty of using these tools is that separation logic intertwines reasoning about pointers and memory with reasoning about the functional behavior of a program. Our work aims to disentangle this reasoning by automatically extracting a functional version of the imperative code without the pointer reasoning. We call these functional specifications. The approach of relating an implementation code and a higher order functional specification, possibly using intermediate specifications, is pretty standard. But we hope to reduce the effort required to do this by automatically completing part of it. After extracting our functional specification, it should be easier to show that it refines the desired high-level specification. We do this using a type system like that of Rust, which disallows dangerous pointer aliasing, like this example. By doing so, it guarantees memory safety. The key idea of this work is that well-typed imperative programs in this type system should have equivalent functional programs. The type system uses ideas from separation logic and, in effect, handles all reasoning about pointers, leaving only the functional behavior of the code in the extracted functional program. One caveat is that sometimes memory safety does depend on the functional behavior of the code, such as indexing into arrays. Balance checking, we defer to the functional spec by having the extraction process convert cases like this into dynamic checks in the specification, where they later can be proven to never reach an error. Additionally, since the type system is so restrictive, it can't type check some programs that one can verify with separation logic. Similarly to how in Rust, one sometimes has to use unsafe blocks to write especially performant code, these programs can't be typed in their type system. Intuitively, we're targeting the simpler code, which is also the majority of code out there, code that's already fairly easy to translate into a functional specification by hand, but it's tedious to do so. The project has two main parts. First, we have a verification tool called Heapster, which applies this technique to extract calc functions from LLVM intermediate representation, given that this input code is well typed by user-provided type annotations. Secondly, we formalize this type system in calc and prove it sound, formally relating properties of the input imperative program and the extracted functional program. Let's go over an example for how this type checking / extraction process works. For the input code, consider this linked list data structure in C and a function that computes the length of a linked list. As for type annotations, we need to first define the Heapster type for describing pointers to list structs. This type will encode our assumptions about the function argument, and by doing so, ensure that the function is memory safe. The list type is a pretty straightforward translation from the list struct. It's a recursive type that then uses a disjunction to represent whether the pointer is null. If it's not null, then it must point to a list struct, which has an int64 as its first member, and recursively another pointer to a list struct as its second member, which resides in memory at an offset of 8 bytes. Note that this type restricts the set of possible executions. The argument is assumed to be well-formed, without invalid pointers or circularity. That's partly enforced by the star, or separating conjunction, from separation logic, which ensures that we don't have multiple aliasing mutable pointers. Generally, Heapster types describe the shape of the value in memory, along with the permissions of the value, what it's allowed to do. For example, we could augment this list type with information about the pointer being read-only, since the function, the length function, doesn't need to write to any memory using pointers. What's crucial is that types don't need to contain any more information about the behavior of the code. There are no specs hidden in these types. Now we can provide the type annotations for the function. The argument has type list, and the return value has type int64. Looking now at the implementation of the function, which loops through the linked list, the user must also provide a loop invariant as a type annotation. Here, the loop invariant is pretty simple. List has type list, and n has type int64. We have some ongoing work which aims to automate this step of finding the loop invariant in a lot of common cases. During type checking, the functional specification is simultaneously extracted, so we'll also describe the type of that functional program. To represent a list in the extracted spec, we use the heapster type from earlier and perform a simple translation. The recursive type remains, but equality types are erased, since they're only used for type checking. The equality type is represented in the spec by the unit type. Disjunctions are translated into sum types, and pointer types are also erased, represented by the translation of the type of their contents. The separating conjunction is translated to a product type, so in the end, on the right side of the sum type, we get an int64 and recursively another list. The resulting type, list S, where S stands for spec, is isomorphic to the standard list type. Then, for the type of the entire function, we follow the same translation, except that the output is in a monad M that I won't go into in this talk, but this monad is needed to support errors and iteration in the spec. Now that we have the input code, the type annotations, and the type of the extracted spec, we can proceed with type checking the imperative code. Defining the variable n adds a type for it in the context. As with all mutable variables in the implementation side, it's erased in the functional program. Next, we have the while loop, which translates to an invocation of iter. Iter is a higher order function that repeats a function body with some given inputs until it terminates. This function body takes two arguments, which we get by translating the loop invariant types, which are a list s and an int64. These correspond to list and n on the imperative side. The initial arguments of the iteration are given by the initial values of the corresponding variables in the while loop, which are the argument to the function, L in this case, and 0. Now for the body of the while loop. First, we unfold the recursive type in order to case split on the disjunction. On the specification side, this corresponds to an analogous unfolding and case split on the value of type list s. On the left side of the disjunction, we have that list has type equal to null, which after this return statement, that type gets dropped, and we obtain the return type of the function as required by the original type annotation given by the user. A corresponding return is extracted to the specification side. On the right side of the disjunction, we have that list has a pointer type to a structure with two fields. On the specification side, this is the right side of the sum type with the corresponding two fields. Next, on the imperative side, we update list and n, resulting in types that satisfy the loop invariant for the next iteration. On the specification side, we continue with the next iteration as well, this time of the loop of the function body using iter. The same changes we made in the imperative program are translated to the specification. With that, we now have a functional program that just iterates through a functional list without any pointer reasoning, concluding the type checking and extraction process. Since the spec is just a function in Coq, we can also prove whatever properties we want about it. And as we'll see next, those proofs also give guarantees about the original program as well. To prove the soundness of this approach in Coq, we use semantic type soundness. Though I won't go into details in this talk, the majority of the paper actually deals with the meta theory of the type system. We represent the semantic interpretation of a heapster type as rely guarantee relations, which describe how the types restrict side effects in the program. The typing relation we interpret as a bisimulation, which relate the imperative and functional programs with respect to the interpretation of their type. To account for dynamic checks that might be inserted in the specification, the bisimulation also allows for error computations, but only on the specification side. Finally, we can prove the typing rules of the type system as lemmas using the semantic interpretation we just defined. Using these definitions and results, we then obtain our soundness theorem, which states that if the two programs are well typed, and if the functional specification can't step to an error, then neither can the original imperative program. The slogan here is, well-typed imperative programs can't go wrong, as long as the extracted specification can't go wrong. In addition to this, we also proved that formulas from a fragment of computation tree logic are shown to be equisatisfiable by the two programs, under the same conditions as earlier. This means that we can prove temporal properties, such as liveness or fairness for the specification, and obtain that same result for the imperative program. Now, back to the Heapster tool. The tool is still under development, but we have some early results using it for part of a realistic C project dealing with this mbox data structure. It represents network packets from the IPsec protocol for encrypted communication. We implemented some functions for handling mboxes, and were able to successfully type check most of them by providing the input and output types, as well as loop invariants, just like we did in the example. The 4 functions at the top that we couldn't type check all use low-level features that the tool doesn't support. Of the ones that we did type check, for 7 of them, we also proved higher level properties of the extracted specification, like safety and functional correctness. But even without doing this, without writing proofs about the extracted specifications, just using Heapster to type check the code has helped us find bugs, such as missing null checks and incorrect array indexing. These sort of errors result in type checking errors, which indicate that the memory is somehow being used improperly. If you want to know more, please check out our paper. It includes a lot more detail about the semantics of the type system, which are built upon rely guarantee permissions, a novel semantics for separation logic. The paper will also describe support for other language features that weren't in our example, like memory management and arrays, which require adding dynamic checks to the code. It also includes details about the Heapster workflow, with concrete examples of what the specs and types look like, and how we use the extracted specifications in Coq. To sum up, our type system restricts imperative programs to act in a memory-safe way. This allows the type checking process to extract a functional program with provably equivalent behavior, but with dynamic checks inserted for behaviors that threaten memory safety, such as array indexing. We have both a Coq formalization of the meta theory and implementation of the type system, which takes imperative programs in LLVM IR and extracts functions in Coq. Both developments are open source. Thank you very much for listening. If you're at Oops Alive, I'll be here to take questions at the end of the session.